Hello, hello, welcome. Hello, welcome. Welcome to Code is Craft. If this is the first time you've been here, this is our semi-regular series of speakers who come talk about things code and craft, and both. If you are not already following us on Twitter, I recommend you do so. Code as Craft is our Twitter handle. Codeascraft.com is our engineering blog. You can also sign up for a mailing list to hear more about these sorts of events when they come up. At Etsy, one of the things we like to invest a lot in is our tools and automation. It's always fun to hear about how other companies are doing that as well, and of course, it's always fun to hear about the sorts of stories that only happen at a place once you reach a certain amount of scale. So we're real excited to have Shlomo here tonight to talk about how they're doing some of that stuff at Facebook.
Hello. Hey guys, my name is Shlomo Priymak, and I flew in here today, or yesterday rather, from San Francisco to discover a wonderful weather here as well, which is always nice. Can you hear me okay? Yeah. The other one? Hello? Yes? All right. All right, perfect. All right, so I flew to here so that I can talk to you about how Facebook backs up its data, which is a subject that's not always very sexy. People don't like talking about backups, but it gets way more interesting if you have a lot of data. So most of the talk is going to include a lot of information about MySQL. How many people here have experience with MySQL? Or awesome, excellent, okay. Great. So I'm going to be referencing various internal things and so on for the entire talk. So Facebook has 4 different teams that work on MySQL. We have, and I'll go like from the top of the stack to the bottom sort of. So like we have the database client team. They deal with various things relating to the database client, discovery, automation around how to connect to various instances and so on. We have our performance team, which deals with, they're the closest thing to DBAs, so they deal with things like performance issues, actual things like why is my database being slow, figuring out why specific queries are slow, analyzing traffic patterns, and so on. We have our database engineering team who actually write our own patch of MySQL. So if you ever heard of WebScale SQL, maybe? Some people here are nodding. Okay, awesome. So we actually use a patch set on top of that, which is our own patches, which is also freely available. This team works on this version of MySQL. And last but not least is, why is this? Sorry. Last but not least, the team I'm on, which is the MySQL infrastructure team. We're 12 people spread out throughout the world. We have half the team in Dublin, the other half is in California. I'm managing the California half of the team. And that's about it. We're 12 people doing all the operational part of managing MySQL. We build the code, we make sure servers go up, we write all the automation that manages everything. So why do we even have this many people at Facebook working on MySQL? Well, MySQL is centric to everything Facebook does. So our entire social graph, like your friends, your likes, your comments, all of the financial data Facebook handles internally for various, I don't know if you, I guess you don't do that anymore, but if you had Farmville accounts, like every single message you send on Facebook, if you use Messenger, goes through MySQL, which is probably a surprise for most of you guys, but it's the most reliable and effective solution for this sort of work. So since we have so much of this data, we have to make sure we not only manage it, but also back it up in a way that's reliable and stable and so on. So this talk is going to be layered in a sort of logical ways. So I'm going to first talk to you about how Facebook uses MySQL, how we lay out our servers and our data across all of our servers, introduce some backup fundamentals, talk about some challenges we have, and various war stories sprinkled in between, and then about the design of the system that we've designed to replace what we used to have. All right, so MySQL Facebook. As I said, we have tons of data. How do you handle a huge amount of data? What is the classic way? Someone has to yell that word. Sharding, exactly. Sharding. So we use sharding. For sharding of our largest data set, we have something called FBID. So we took the 64-bit range and we divided it into sub-ranges, and every shard gets a sub-range. And then we have functionality that maps this FBID to the range where you might find it. And we do this similarly for various things in the system. And often people say, well, what is going to happen when you run out of numbers? It's a very common way to troll people that are new, but 64 bits is a huge range. So there's plenty for everyone. And you can see these numbers, like if you use the Facebook Graph API, you'll see some IDs. These are equivalent to like FBIDs. I think these are actually anonymized or something, but that's just the point. That number is made up, there's no... All right, so how do we actually put these shards on servers? So at Facebook, we don't run our servers as, we don't have any virtualization systems. We just use pure metal, and we run multiple MySQL instances on those servers. So what does it mean, MySQL instance? It's just a server bound to a specific port, and we just run multiple of them. It's a very common thing. Many companies do that. If you were running on Amazon, AWS, or whatever, it would be more convenient because you can just spin up another instance. For us, on very large hosts which are efficient, it's better to just do it ourselves. And for every single host, we just, the MySQL databases, we just call them shards. And they, of course, don't live by themselves. They exist usually inside of a replica set, which is a word that I thought I made up, but apparently MongoDB made it up before that, perhaps. But it doesn't matter, replica chain, whatever you want to call it. And we have very significant amounts of automation that run these replica sets. So in a replica set such as this, if you're not familiar with MySQL, you always have one node which is called the master. The master takes all the writes, and you have the slaves which take all the reads. So we have many of these slaves. And we spread them out for, again, our largest system. Different systems can have different configurations across the world. So this is the most recent map of our announced data centers. So we don't actually have, this has been announced, it's not done yet. We're working on this one, but it's all been announced. We have replication in various locations across the world. Even all the way up there in Sweden, where it's very cold. And it's great for servers, because it's cold. So we have replicas of our data all across the world, and it's going to come into play when I talk a bit about backups. You'll see how we take that into consideration. And we have a lot of servers. When I talk about a lot of servers, we have a lot. So we used to have, we could say thousands, now I can say 10,000s of servers. It's a lot of machines. It's a tremendous amount of machines. Whenever I say tremendous, I think of Trump. Tremendous. We have servers, we have the best servers. So kind of try imagining what does 10,000 server mean. So how many servers do you see in this photo? This is a publicly available photo from the Facebook page of the Luleå data center. So this is, this is about half of that. It's about 100 servers in this picture. So, and every one of these racks is like huge. It's taller than me. It's very deep. It consumes a lot of power. And all you have like in this photo is like 100 machines. I don't count the ones on the bottom here, but these are actually our old database racks. This is a pretty old photo. But so this is 1,000 machines. Quite a lot. It would take probably this entire stage to store them. But how many servers do you see in this photo? Maybe like 1,000, a bit more, right? Like 1,300. I tried counting them, I gave up. It's a lot of machines, but you need a lot of space to store this, and this is like half a row of servers. So in our data centers, which are publicly available, you need, like all the designs are publicly available for them, so you can actually go and see online how we do this. But we have huge rooms like this, where we store all this stuff. And the awesome thing about working on Facebook is that I get to go to these places once in a while. The last team offsite we had, we flew to Altoona, and we just toured around one of the data centers to kind of get a feel about what it means when you have to manage this amount of servers. You have to understand what it means for people on the ground actually running these systems in production. And the cool thing is that this is like one room, right? So if you want to store a lot of servers in one location, this is a building I don't know if you guys ever seen these photos, but this is one building out of multiple that you have in one region, and that photo I showed you before was a partial shot of one of the rooms. So it's a huge scale. Like you can see there's a truck here. This is like big, huge ass truck. This is like SUVs, right? So these are generators and so on. This is a huge building. It takes like 5-7 minutes to drive around it, which I've done. It's humongous. So it brings with it various interesting challenges. Of course, not all of it is filled with our servers, but there's other machines there, but kind of get a feel of the scale. So now that I've sufficiently wowed you with pictures of machines, let's talk about backups. So how do we back up our databases? So this might surprise a few people, but we use MySQL dump. We just generate logical backups of the data. We use single transaction, which makes sure we get a consistent snapshot, and we copy the entire data using MySQL dump and store it somewhere. Our version of MySQL dump is slightly different. We use a logical read ahead, which is a patch that we've done to help disk systems to be more efficient. It kind of prefetches pages and makes sure we read them in order from disk. Just some efficiency improvement, but it's pretty much the same thing. So some people are wondering, why are we doing logical dumps? Hopefully someone is wondering. So I have a slide just for that. Because usually someone asks, like, why do you do logical? Why don't you just copy the data away? You know, right? Like you do use LVM snapshot, you use NetApp snapshots, whatever it is you're running with. So, and here's a nice chart showing why this is the solution we chose. So first of all, if you want to read logical backups using any tool, let's say you want to analyze your data and you want to run ETL on it. You want to extract that data because you can just read your backups, right? Why would you need to scan your databases for that? You can read that using any external tool. You can use Vim if you want to. The size is going to be far smaller since it compresses better, which is actually somewhere here. But also the backup itself is smaller. You don't need to backup indexes. It is far easier to restore a single table because you can just read the file and get the place you want, which is much harder if you're using InnoDB, hot backup and stuff like that. And if you have a corruption, it's much easier to work with a text file that has some place that's corrupted versus logical, like a physical copy of the data. So it compresses better, and the only downside of using logical backups is the fact that it takes longer to restore, far longer, right? Because you don't just copy the data over, you need to rebuild everything. That's the only downside, but we worked around it. We just have fast systems, very fast servers. Another thing we back up is binary logs. So those that are not familiar with MySQL, binary logs contain all the changes that happen to a database, to the master throughout time. So like every statement that happens, it's registered in the binary log. So it helps you do point-in-time recovery. You recover to a certain point in time using your full backup, and then you roll forward using your binary logs. We also rolled out global transaction IDs. This is more relevant if you're some sort of DBA, but it just helps identify transactions more easily instead of your backup. This used to be something that was hard to move towards. We were one of the first companies that did that. We modified MySQL a bit to like have some rollout plan, but in 5.7 you can actually do it yourself in an easier way. So we have dumps, we have the binary logs. So how do we back things up? Well, we dump everything every single day. And if you think about it now, right? I showed you all these servers, right, holding all that data. It's a lot of data to dump, right? It's a huge data set that you need to basically back up every day. And we back up all of that, and we back up all the changes that happened. And we back it up to we have multiple stages of backups. So our main location, the first location for backups is HDFS. It's great because it's just cheap and easy to kind of run it. It has a lot of space, easy to work with, sort of, and you can run MapReduce on it in order to extract things using ETL, various ETL tools, right? And we have another backup system that's offsite, and I'm not going to even mention it apart from what I did just now. So we did the backups, and then we have a separate system that does the next phase of backing up, which is a continuous restore. So this is exactly what you might imagine. You continuously restore. things. So for every single shard we have, and we have lots of them, we have a system that runs on like few hundred machines, and it reads the shard, reads all the data, rolls forward binary logs, and restores it to a certain point in time. So you can make sure that you actually read that and read your backups, not just hope they're there and going to work at some point. One of the interesting side effects of having a system like that is the fact that you can, by improving the speed at which this system restores things, you can improve your restore time in actual production scenario where you have an emergency, right? So instead of testing it when something breaks, you can optimize the system and make sure that your continuous restore is working faster. That's going to mean that all your backups, if you need to restore them in an emergency, is also going to work faster. So we use this sort of methodology to make sure that if something bad happens, we're going to be prepared. So next thing I want to talk about, now after we establish kind of the cadence of what we back up, something called differential backup. So I've mentioned that we have a large amount of data which probably needs a lot of storage and HDFS to store it. This can be cost prohibitive if you want to store more than a few days, right? Because you need a copy of your data every single day, which is very, very expensive. So a solution that many database systems have, if you ever worked with SQL Server, someone? Oracle? Wow, okay, awesome. So they have these solutions already. They already support that. They have differential backups, they have all these solutions. But in MySQL, it doesn't exist. So we made one. We made one because we looked at the benefits of using something like this. So this is a graph that shows, honestly, it just shows the fact that differential backups make sense because the amount of data that changes is not that huge in every day compared to your data set. That's all it says. This is the percent of space, and this is your full backup. So assuming your backup slowly grows in size, the differential backups grow slower. It's pretty obvious, I guess. So differential backup is great, but how the hell do you do this in MySQL? MySQL doesn't support this. Other systems, they mark blocks on disk that were changed, or like they keep various maps of changes, and you can generate that diff very efficiently. MySQL doesn't have anything like that. So we had to build something like this in order to save space to have longer retention times. So how did we do that? It's actually far simpler than you might think. So what do you need to generate a differential backup? You need your old backup, which here is represented on the left side, and you need your new backup that you've taken today. And then what you want to do is you want to generate the difference between the 2 days. So if you dump the files in the order of the primary key, you can actually do that. The same way you would generate a diff between two just files on disk, right? You scan the file. If you have no change for the same key, then you do nothing. If the row was updated, you register one deleted row and one inserted row. And if the row was deleted, you just write it in deleted rows and so on. And it's only possible since the data is ordered. Does that make sense? Awesome. So after you're done with something like this, and of course you also log in the rows that were inserted, you get these two files. One registers all the rows that were deleted. One registers all the rows that were inserted. And what do you do if you want to restore your backup now, or rather get your new full backup? So you just run a three-way merge. Right? You get your old full, you get your deleted rows, you get your inserted rows, and you just scan them all at the same time, and you create the full backup dump that you just deleted. And this is great because it allows us to save a lot of money and a lot of servers and power and headache. So we have a cadence similar to this one. So we take a full backup in a certain rotation, right? And then we take a bunch of diffs that are based off of that. And then we take another full backup and then take a bunch of diffs, another full backup and a bunch of diffs, and so on. It just cycles like that. For every shard, it has its own cadence. And this, in theory, works quite well. And we built it. We thought we could just generate all these diffs. So we could just do that on HDFS and not even change anything about how we dump our backups and just save the space. But the problem is, in practice, things don't always work out the way you want them to. So our first solution, like I said, would be to take MySQL, dump the files as before, not modify the system at all. and then run some MapReduce job or something. And by the way, this is why this tool we have, which I call it the differ or whatever, it has its own name, but it's written in Java. We have nothing else in Java. We are like purely Python shop. Like everything we do is Python. Like why would you ever have anything in Java? Well, it's because we thought we might run this on the on the HDFS clusters. So we tried this. And the first test we tried, of course, at any scale that's larger than 0, this just didn't work at all. First of all, it used way too much space on HDFS because you need to write all your backups, and then you need to read all of them. You need to consume a lot of network because HDFS is it's distributed, right? So you need to like get all the blocks from all the different nodes and combine them, and takes a huge amount of network I/O, and also just takes more than 24 hours, which defeats the whole purpose of having a 24-hour backup window, right? So that doesn't work at all. So we came up with something pretty cool. So the thing we did was to identify. I mean, this file, the new full backup, is not actually needed. We're going to throw it out, right? So why even bother writing it into HDFS? So what we've done instead is we do all of this in runtime. So, and this is a pretty neat thing that happens. So we run the backup on MySQL. We dump everything. So MySQL dump is streaming the backup. At the same time, we stream the data from HDFS. We get the old one and decompress it, do all sorts of things. Get that so they both converge. And then in memory, we run this differential backup generator, which writes it back into HDFS. So it's pretty cool. It saves us, I mean, it wouldn't be possible without doing something like this, just using streams. And we actually run this entire thing on the database server, so it can scale with the size of our cluster. So the more servers we have, this thing scales with it. We don't need to like have enough HDFS nodes to do this, or like somehow have dependency between the two. So is anyone worried about running this on the database server? Is anyone thinking it's consuming too many resources, or yes? Okay, it's usually like someone like, oh, something here, like what about memory? No, it's fine, it takes like 100 megs of RAM, it's fine. It's actually pretty cheap. It doesn't actually hold anything in memory because it's all sorted. It doesn't need to, the buffers are not that huge, it's pretty efficient. I know, I was surprised too. All right, so now that I walked you through how we do differential backups, so let's talk about how you design a distributed backup scheduling system. So for that, I'm going to take you a bit back in time into how the system looked like 2 years back, sort of, before we started making changes to it. And sort of which assumptions we had and why it was designed that way. And then what we actually did to change it to make it far more efficient, faster, reliable, all the great words. The first thing to know about backups is that they're heavily reliant on network. Like I said, we have to move our entire data set. Every day we need to back everything up. It's a lot of data. So this slide is actually old, so there's no point of taking photos. It's very, very old. It's even more now. It's the amount of traffic that goes on for the networks is humongous. This is the traffic going into the backup HDFS clusters every day. And there's these huge spikes because we kick off the backups at night when the sun goes over the Pacific. So there's no one actually using Facebook, or like at least less people, except for the guys in Hawaii. But we have like a trough, so we make sure to fill it up. So because the system is using so much network, it was designed in a very specific way around the network structure at the time. So what we had is data centers. Let's say this is the Forest City data center that I showed before in the map. It's in North Carolina. And in a data center, you have multiple buildings. And inside of a building, like I made up, like let's say you have 2 clusters in every building. So this is just a diagram. Like it's not how it actually looks, but for the sake of explanation. So in every single cluster, what we would do is we would back up the databases in that cluster into the HDFS cluster in that cluster, which makes things easier, right? You have databases there, you have very fast network within your cluster. You can transmit a huge amount of data, you don't bother anyone, and it works fine. But of course, it doesn't work perfectly, since if you have such a system, you're not going to be very efficient about how you use your backup HDFS clusters. So in this case, like if you have more databases here, the HDFS is going to be more full. If you have less databases here, it's going to be less full, and so on. You have all this like wasted space here. I tried to show like this is full and this is empty. I don't know if it's not a gradient. It's supposedly showing that this is like more empty. So this is a huge inefficiency, right? Ideally, you would want to use all the clusters equally. So, but this is how the system was built because of various assumptions. So why did we do it this way, or what assumptions kind of led it to look like this? So of course, the first thing is network is too slow. Fine, that seems like a reasonable thing. It's a huge amount of data to copy every day. And then we had other assumptions, like we have our fastest hardware in this data center. We had like flash the servers there very fast. It's easy to take backups on them, great. Scheduling, we thought that it's very hard to schedule backups to make sure they all happen. We didn't want to risk it. If you just back up into the HDFS cluster in your cluster, there's nothing to think about. It just goes from one to the other, very easy. And we didn't want to back up from slaves, because who the hell knows, maybe the slave is lagging. Maybe it's broken, like it wasn't reliable enough to rely on that. But the thing is, like all these assumptions that I just went over, they weren't true at that point. We actually had our oldest hardware in the data center at that point. We had way more data centers. Scheduling is not that hard, or at least I believed it wasn't hard, so we kicked off the project to change this and like order different hardware and all that before I actually was sure how to write it. But it seemed like it could be solved. And then at this point also the assumption that we can back up from slaves also wasn't true. I don't even know what that was the case. So the only thing that was left was network. So we say, okay, let's see if we can make the network better. We heard there are improvements and so on. So we talked to the network guys, and since Facebook had more advanced network at that point, we upgraded a few switches and stuff like that, and they're like, yeah, it's fine. Do whatever you want. So, like, great. So now that we don't have any of these assumptions anymore, we can do things in other ways. So this is also no longer true. So now we can do whatever we want. Network is not a limitation as long as you're within the same region. So now let's go back to the map. So we have data centers all over the world, and some of them, I can't say which ones, but some of them have HDFS clusters for backup, some of them do not. And the servers have different distances, you have different bandwidth between different data centers, different sort of latencies and so on. So you need to take all these things into account when you decide where to run the backup and where to back up from or where to back up to. So you need to choose your target, that is where you write your backups, and you need to choose the source, that is which one of the replicas, right? I mentioned we had many of them located all over the world. So we have all these replicas, we need to decide which one is actually going to do the backup. So what are our goals when we design a system like this? So first of all, we want to make sure we use our hardware efficiently. HDFS clusters, even though HDFS is like, makes things cheaper, it's actually still pretty expensive. If you have tens of thousands of servers of databases, you also have thousands of servers that are running the backup clusters, right? It has to be a certain percentage of it, and it grows with it. So it's very important to be efficient about how we use it. So that's the biggest win from that. The other thing is minimizing cross-region traffic, which I mentioned before. You can't just start copying the dataset like from the West Coast to the East Coast or to Sweden. Like, you just can't do that. You don't have enough capacity. You're not going to be done. We need to make sure that when we choose where to back up from, we're going to choose replicas that are not broken. So if you have a machine that is not functioning, you don't want to back up something that's like not up to date or not even going to run it, and so on. And this is an interesting one. You want the system to be consistent. So you don't want the backup to be one day running here, the other day running there, like, or all of your servers all of a sudden deciding to back up in one place. Like, you want it to be very, very stable, and you want change to occur slowly. And you'll see why, by the way. I'll get like to the war stories part. You'll see why you want change to happen very, very incrementally. Because a system of this size, it's like steering the Titanic. You kind of start turning the wheel, and you wait, and you like, I have no idea if it turned. And you need to wait for 2 days before you're like, oh yes, yeah, it seems to be like going starboard or whatever. It's really strange. So it needs to be like stable and not misbehave. And of course, you need to back up at least once. So, of course, right? If you back up more than once, that's fine. But less than once, less good. All right, so We designed a distribution algorithm that would determine the target. So not where you back up from, but just which HFS cluster you're going to go to. So what we do is we define the allocation rules globally, and then we store it we store it in something equivalent to Zookeeper, which is just all the servers can access it. So it's like one source of truth, shared configuration, and then we hash all the shards into like 1,000 buckets. I chose 1,000 because I wanted to have a promille of accuracy. So I can say where something goes, up to like 1/10 of a percent, no need for more. And then we allocate these buckets to clusters proportional to their size. So I'm going to now say this exact same thing while I have pictures here. I don't have puppets, but pictures are good enough. So let's say this is a server and has 14 shards on it. So you just hash the shards into 1,000 buckets, and let's say there's only room for 8, but let's say it's 1,000, and they just get spread out throughout this buckets using something fairly simple, like just hashing function modulo on it. It's fairly easy. And then in this example, let's say you have a 10 petabyte total size of your HDFS clusters, and you have 1,000 buckets, then it's fairly simple. Like if you have a 1 petabyte HDFS cluster, then you get 100 shards. If you have a 2.5 petabyte cluster, it gets 250 shards and so on. Sorry, not shards, but buckets. Make sense? Right, and then when backups occur, shards in that range, like buckets 20 and 30, are going to go to this range, 200, 400 to this one, and so on. Right, they're all going to just go to where they belong. So you can, with like nice accuracy, kind of say, okay, like I'm going to shift this percentage of backups from here to there. You can control this in a very high resolution, up to 1/10 of a percent of your entire pool. And when I say pool, I mean pool. Now all of our servers are basically treated as one huge pool. We don't need to think about which ones are going to be used more or less. They're all going to be somehow automatically managed. Great. So I'm going to do a short detour for a tiny war story. So after we deploy this, something unexpected happened. This cluster, you see that it's misbehaving. Like these ones are fine, right? They're very close in their allocation. This is utilization percent, and this is time. All right, so these guys are kind of equal, and this one is not very happy. Why is more stuff going there? We were like very surprised by this, tried to analyze this, and then I brought this cluster up. Later on, this went down, but this one didn't. Like, what the hell is going on? Like, the sharding should work. Like, I designed all this. I checked all the numbers a million times. Well, then I ran some numbers on our distribution, and guess what? You need to pick your hashing function properly. This is Python hash. So if you look at the sorted version, it's not that great, right? Or rather, it sort of looks okay, like it has a big divergence. But if you look at this, like look at this range, it's far, far lower. So if you have a cluster allocated to like this range, you're kind of screwed. So what do you think we did instead? Instead of using the Python hash function, what did we switch to? We switched to MD5 and then just hash them based on that, and that looks much better, right, the way it should be. So choose your hashing functions properly. Yeah, I'm not going to use Python hash ever again. So after that, of course, things got better, and our cluster sizes converged, and now they're all kind of the same, like we expect them to be. All right, so we talked a bunch about how we choose the target, right? We know how we hash everything, we put into buckets, we know how to pick which HDFS cluster data goes into. So how do we choose where to copy it from? So let's use this example. Let's say you have a replica set with 3 sources, possible sources, A, B, and C. So let's say you somehow get from above, you get some priority list for all of them. And the way you get this is you run an algorithm on that source of truth that I mentioned earlier, right? In Zookeeper, you have the configuration. It says which the best destination is. And now every single one of these machines decides for itself whether it should back into that destination. How does it decide that? Using this priority list. I'll show you how it's generated, but let's say you already have this. So this list says C is the first one to be backed up. Then if C is not there, then A, then B.
So A goes on the list in order. So if it sees a C there and it connects to C, and C is fine, then it says, oh, I'm not going to back up. C is alive and seems okay. It's going to take care of it, no problem. But then, if C is not alive, then A is going to say, well, then I should do the backup. Like I'm the one. It's like it takes over, feels a sense of urgency and responsibility, and performs the backup. So, how do we determine this priority list? How do we decide which one is more important than others, which one should be backing up, and where, and so on? So I'm going to have to use like some Greek letters in this example, since it makes things kind of easier. I don't want to like get numbers into it, but let's say, so I said before, we don't have an HDFS cluster in every location, right? But some of them do have HDFS clusters. So for this sample replica set, we have, for replica A, we have a cluster in this location, cluster alpha. And for replica C, we have a cluster gamma. And then we need to define like a cost function. You need to say how expensive is it to perform the backup. So in this case, since it's in the same region, it's 0, right? If you copy it within the region, we said network is cheap. Same thing here. Network is very cheap, so the cost is 0 to back up to this cluster. But if you want to back up between the two, I've defined arbitrary costs here, just for the sake of the example, right? So you have various numbers here that say how much it costs. And then you can use that in your ranking. Another thing we define is a priority list for the clusters. So you want to say, you know, you are defined according to the map to perform the backup in this location. But if it doesn't work out, you know, you can also use that one as a fallback. So once you define all these things, you define the priority list for the clusters, you define the distances and so on. What you do is you actually do a very simple ranking function on this data. So your ranking function is going to look something like this. It will take your MySQL instance and the HDFS cluster, and it just output some sort where it first looks at the distance and then it looks at the priority. And this is oversimplification. Of course, the code doesn't look like this, but it's sort of the same idea. So then, what you do is you do a Cartesian join of all the different options that you have in there, and then you just sort them by that. So it may look like complex, but actually fairly simple. All you do is you sort all your possible options according to your ranking function. That's all. Sorry, I'm a DBA, so Cartesian joins are like, of course, that's the easiest way to understand something. So let's say this is your data, right? And it contains all the different tuples, right? So A and alpha, A and gamma, and all these combinations. So you sort the data, and you get something that actually makes a lot of sense. So now let's see how this looks like if we look at the graph. And I just took this and copied it to the next slide. So here's the same list here. So now it's going to make a ton of sense. You look at the first one. It says copy C to gamma. Why? Gamma is our first priority cluster, and C is the closest thing to it. It makes sense to back it up there first. What happens if C is dead? A will back up somewhere. Why A and why to alpha? Because alpha is second priority, which is fine, but it's also cost of 0. And then if both of these guys are dead, then your only option is to use B to back up to gamma, since it's lower cost than backing it up. To alpha, because it's a lower cost than backing up to gamma. Very simple. Like this sort of simplification kind of makes it a more general case and cover all the things instead of writing a lot of different functions that kind of cater to all sorts of edge cases. This kind of simplifies this. So the system mostly works. Sometimes it doesn't. I mean, it's just code, right? Even if we're crafty with it. So what happens when things don't work out well? So let's say your function to determine health is not working correctly. So this is a case that actually happened to us. So you have your replica set, A, B, and C, my favorite ones. And we started backup on node C. The problem with this specific replica set is that it ran a system that didn't work well with backups. It was a very big replica set. If you run a backup there, it just couldn't handle the load. So what happened is it caused the slave to lag. great, slave is lagging. It's not the end of the world, right? But the system the detection algorithm was like, oh, if slave is lagging, then I guess something is broken. Let me start another backup, because I think C is not handling this well. So starts another one on B. And then let's say you had 5 more of them, it starts a backup on every single one. And then in the end, it starts a backup on the master, because they're all busy backing up. So you have the replica that everyone is backing up like very urgently, but nothing is working. So luckily it wasn't anything that's like available for production. No one could see this, but it still happened. All right. So that's it for explanations about how backups can work in general. And now it's the interesting part of war stories and a bit what it means to work with a system of this scale. So I have 2 stories here related to the same issue, turning up a new cluster. So this was the first time we actually turned up a cluster in the new region. It was a new cluster. For the first time, it would be in a different place, like on the West Coast versus East Coast, like all sorts of things. But this was the real like field test for the system to make sure that all this stuff that I just did with like, letters and all that would actually work. So we have a new data center available for this, and then we start a slow ramp up. So I turned it up like, 0.5%, seems okay. I turned up to 1%, bam. We have engineers like from network team like, what the hell are you guys doing? You're breaking the network, like our cross American and North America links are like oversaturated. What is going on? And we start looking at the data in the networking systems, and what we see is the data is being pulled from HDFS into MySQL. Like, what the hell is going on here? This is a backup system. We're not, like, what? That doesn't make any sense. Why are the machines there reading, like, so this was very confusing for a bit, but then we realized what was going on here. So remember I told you about differential backups? So the system was pulling backups from across the country to create the new dumps. And this was just 1% or like a tiny percentage of the backups that already like kind of felt this load. So this is why I'm saying it's kind of like the Titanic. You kind of move it a bit and then you don't know where it's gonna go. I guess Titanic is not a good example. Maybe some big ship. So we had a good fix for this. The fix was just to, whenever you change your destination, you just back up to, you just create a new full backup. You just don't generate a diff if the source is different, just to be sure. It kind of resets the cycle and everything is fine. Easy. Great. So we fixed this bug. I'm like, excellent, everything's gonna work awesome. And then, I started slowly turning things up. So I did like 1%, 5%, 10%. It seems okay. No one in the network is complaining. We're like, network is fine. Excellent. Let's, change it to 100%, just roll it out. So I come in the morning, it's like 8 a.m., I switch it up, I look at all the systems, everything seems fine. Like, everyone inspect this, yeah, the graph seems okay, networking is fine, we're all happy. None of our things shows any issues. So then we get a call from what I like to call the engine room. So when I said the engine room, what I mean is site ops. So site ops are the guys who sit in those huge buildings that I showed you before. They sit there, there's lots of people in every building that are responsible for our systems, and they actually run the servers. So they message us on IRC, they're like, so one of the guys was working in the electrical room, and he started hearing a very large hum from one of the circuit breakers. So a circuit breaker in data center, it's not like, like what you have at home, it's like, oh, let me turn off the power to the TV or whatever. It's like, it's the size of the stage, it's humongous, it's like twice my height, it costs millions of dollars, it carries megawatts of power through it. So when this thing starts to hum, it's very, very scary. I've been near them, they're humongous things. So, and then they're like, yeah, if you're using too much power, so if you continue using more power, we'll have the risk of de-energizing. Well, it sounds a bit like Star Trek, but that just means we're gonna lose power to some of your rows because we just don't have power. So that's not good. Of course, they have various protections in place, and it will turn out some gracefully, yada yada. It's all very. There's lots of layers of protection in that case, but at least that's what they told us, right? So we had to solve this somehow. But first we need to understand what happened here. Why the hell were we using all that power? So Can anyone guess? Yes. So the issue with that is that when you plan out a data center, and this is one of the things that if you like using Amazon, you'll never have to worry about. Right? But when you plan out a data center, you need to think about things like power. You need to think about, okay, I'm going to put my servers somewhere, and I need to plan the power consumption. So you say, okay, in this region, we know that servers that run here are going to run backups. So when you plan out your rows, and when they build the data center, they plan the row capacity, they calculate a certain amount of power for every single rack. So every single rack would have a certain power budget. So in that data center, they just didn't count for it. They were not prepared to be running backups there. They didn't think about it. They didn't have this spike overnight. So just it caught everyone by surprise. Luckily, we had a very simple solution. We just had an emergency meeting with them. We looked at we have like amazing like automation. You can see like all the clusters and where things are, which racks, how much power they consume and all that. So we just take a look at the distribution of the rows and we're like, oh yeah, like there's a rack of web servers there. We don't care about those. We just turn them off. And not a problem. We have enough power to run everything safely and kind of remove the load from that circuit breaker. So that's cool. But what are we going to do with this in the future? And we have some cool ideas. So everything I kind of just talked about, a lot of this is going to become completely irrelevant. We're going to switch to a new system that's going to prevent us from going through like all these pains of running backups overnight and all that. How? How, you might ask? So let me tell you. So what we're going to do is we're going to switch to row-based binary logs. We already have this deployed in some places, but the systems that use this for backups are not ready yet. So what is the row-based binary log? So normal MySQL logs, they use statement-based replication, right? They record every single statement that happens. If you wrote an insert statement, you're going to have insert statement in the log. Row-based binary logs records the changes per row. So in a sense, it's like a tiny, 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 tiny diff, right? So what happens if you combine the multiple different diffs, right? You have the previous value, you have the new one, so you can combine them and kind of compress them and you get a diff. But we already talked about diffs. You can take a full backup and then apply diffs to it. Then you would have another full. And you can do this without ever connecting to the MySQL server. You can just do it offline. All we need to do then is test things. So in theory, we could just run our backups once, like for the last time, and then just automate, and everything would just run completely offline, not even touching the servers, no network spikes, no power usage, like everything is just going to be easy and simple. But we're not there yet. We're really going to get there as soon as we can. Yeah, that's it. Thank you very much for inviting me. Open for questions. Yeah.
How much data are we talking?
I'm not at the liberty to discuss that. A lot. Yes.
Is there a reason that, there's obviously a reason that you chose to use MySQL over?
Sure. Could you get into the reasons as to why you chose MySQL over other flavors of SQL like Postgres?
So this decision was made, you can say, by Zuckerberg in his dorm room when he decided to use MySQL. A long time ago, and it kind of grew from there. But to be honest, like MySQL has never really been a problem for us. Like if you automate things around it properly, it's very stable, it's incredibly efficient. There have been projects to try and replace MySQL. None of them was very successful. It's very good at what it does, especially if you have a team of like really good engineers that kind of hack on it, and you have proper operations built out around it. We have so much code that runs all this stuff, right? Like what our team does is we write all this automation that otherwise you would need to create in a different system. So MySQL was like never the problem. We're actually going to replace the engine that we run under MySQL and keep MySQL itself. If you has anyone heard of MyRocks? So, RocksDB? So it's like an evolution that Facebook took LevelDB by Google and wrote a new system that's called RocksDB on top of it. It's very, very fast. It's way better for Flash, and we're replacing InnoDB instead of MySQL with that system, and we're open sourcing that as well. So you gotta check it out if you have, yeah. Sorry, his hand was.
I was just curious, the code for MySQL, it's open source, so do you customize MySQL a lot by rewriting parts of it to suit your needs?
Yes, so we have a patch set.
Like on a regular basis?
Yes, so we do modify MySQL. You can find all that online, you can see all the patches we have for it. A lot of it is to ease automation. Like one of the settings we have is something called super read-only, that you can set read-only to a server, but make sure that even someone with a super privilege can try to ease promotions. Or we have the ability to set read-only for a database, for example, to a shard, right? Something you can't do in normal MySQL. For various things we need. And also we added things like DocStore, which I don't know if anyone uses that much, and again, like MyRocks. We can only do these things if we modify the source. We also fixed a lot of bugs, which Oracle refuses to take back, unfortunately, because of various reasons, because Oracle. So we really want to give them back our code and tell them, hey, like we fixed all this stuff, we want to contribute it back, but it's kind of hard because of various legal reasons to actually take it. So that's another reason. Yes?
Yeah, how does the European right to be forgotten, does that have any effect on your backups at all?
That's a good question. Yes, we have to expire them at a certain time. Our retention policy is actually very actively looks at this stuff, so we need to make sure we always erase them at a certain time. Yeah, that's a good question.
I have a question.
Yeah.
You showed a few graphs, especially about health of various clusters versus other clusters.
Mm-hmm.
What other systems do you have to alert you of the health of the system overall, and how do you know that it's working correctly or when it's not?
Right. So we have various health metrics on the agents themselves to make sure they're kind of doing the work. Then in addition, we have some things that generate reports and check that everything is actually backed up. So that's like the second layer. And then in addition, we have the continuous restore tier that also takes shards and actually restores them. And so you can check the entire workflow and not just a single agent or some data in a database to make sure things work.
Well.
Yeah. Any more questions? Yeah, I think there's another question. Yeah.
I was wondering if you're familiar with Aurora and what you think of it. It's a flavor of MySQL.
I'm not familiar with it.
They basically promise, I think, 5 times more.
5 times more faster than original MySQL.
Yeah.
Cool.
Okay, I just thought that maybe if you're familiar with MySQL.
Where does PrestoDB come into this stack? Is that like built on top of MySQL, or is there other data living
It uses
elsewhere?
MySQL as a storage engine underneath. Okay. Yeah.
Cool.
Well, if anyone has any more questions, feel free to stick around. There's snacks, there's drinks. We'll be here for a while, and Shlomo will be here to answer any more questions. Thank you so much, Shlomo, for being here.
Thank you.